okay, let me give you a simple example. I have a variable a in the program that I reuse and assign to at multiple points in the program, right? On the other hand, here, if I map a register R1 to certain variables, it may not represent the same variable across the program, right? I may use the same register for multiple different variables at different points of the program, right? So it's not the same thing that's available from the top to bottom. Right? When you talk about a variable and you want to find what value is assigned to it and so on, and or whether it is dead, let us say, you are still talking about things that whose scope is larger, whereas the scope of registers, for example, over here is not that large. We would reassign the register to some other variable after every few instructions, let us say, because we know that it's free. So I think this point will get more clearer if not, but I hope you get the intuition that we are not talking about at the assembly level, we are not really talking in terms of things whose scope is large anyway. Or rather, you would be able to optimize even by looking at a window much more than if you were trying to do this over a larger program. Right? Just a small window was not enough in the previous case, and here many times you would see just by looking in a peephole you would be able to optimize the code significantly, and the benefits you may get with global optimization may not be as much. Not empirical study, you know. So as I said, the intuition is that you are working with smaller blocks of code here. You have made your decisions while generating assembly also within smaller blocks. You have not really made those decisions across different basic blocks, for example, or across procedures. Now if you have made decisions within a block, looking at a block is enough to perform many optimizations. Yes, right. So you know a typical so let's take another cue from what we said about code generation itself. We said we'll first do a one-to-one translation, right? So we are independently looking at different instructions over here, right? Now a peephole would try to combine those independent instructions into a small window, let's say, and try to see if there is some scope of improvement that you have obtained within this. Right? Whereas when you had the program that came from the higher level abstraction of a function, let us say, oh, inside a function you have different flows of control organized into basic blocks and so on. So you came from a level where you had larger scope interaction in the beginning, whereas here you are working with, you came from a place where you have smaller scope interactions to begin with. Yes, correct. So that's the trade-off. So you should have, in that case, typically if you assigned registers while looking at a larger piece of code, you would have done your job, right? Yes, yes. No. So see, okay, I think I should have taught register allocation before if I were to answer your, can we wait for a few more minutes? Yeah. So once you see register allocation, you would see that we actually perform it over a control flow graph. Right? So we would use liveness analysis across control flow graph, across basic blocks to perform register allocation. So whether you can reuse a register in a larger window is a decision that you have already made while performing register allocation. That's what I intend to say. Right? So that decision has already been made while performing register allocation because you performed it over a control flow graph, and now it's okay not to look at such large scopes to begin with. Because whatever you could do across basic blocks, you tried to do once, you had an opportunity and you utilized that opportunity before to perform other optimizations as well as register allocation. Now the idea is, start low level, that's simpler. Yeah. So, but I think please remind me of this. I'll mostly have an example where I would show you that, oh, since you took an example of register allocation, you already allocated registers by taking care of the fact that this register can be reused across basic blocks. So there is no point right now starting from that level once more when you know that performing such analysis is costlier than just performing small people optimizations. Make sense? Okay. Any other questions? Okay. So now There are some examples here. You have already seen many of them. Let's say redundant load store elimination. If I have an instruction sequence like this, you are loading a memory address into a register and then you are storing that register's content again to the same memory location. So now you can just replace it with just the load. You don't need to perform this store over here, right? So can you always delete that instruction though? Yeah, let's say no change happened. So these two instructions are my peephole. Let's say my window size, I am just looking at sequences of 2 instructions and nothing happens in between. Can you still safely delete the second instruction always? So even the idea here is, even with peephole optimizations, you have to look at, you can't just keep replacing patterns with each other. There are certain constraints that you need to satisfy. Let's look at some examples. So can I always store, if I anywhere in my program, if I see these kind of instructions where there is the same register here, there is the same variable here, or the same memory location or address here, can I always remove the second one? That's a, you would see what kinds of constraints we would have with this example. Let's say there is something more that could be there in this instruction. That's a hint. Have you, when you generated 3 address code, did you look at labels? You have labels to certain instructions, right? Yeah, so now a hint. Can you figure out something now with this? If there was a label to the store instruction, let's say L2, there was a label L2 for the second instruction. Can you still just look at the peephole and remove the second instruction? Why? There should not be anybody else jumping to that instruction directly. Otherwise, you may have created a problem here, because somebody may have jumped in and stored that value. At that time, whatever is the value stored in R0 will get stored into the variable A, right? So if there is a label on the store instruction, unless you again expand your scope, Jayashree, again unless you again look at the other parts of the program and figure out that nobody is jumping to this label, there is no go to L2 instruction generated anywhere, let us say. Unless you do this analysis, you cannot remove the instruction. If you still want to limit yourself to a peephole, let's say that, oh fine, we always know that increasing the scope of the analysis may lead to more opportunities, but what if I don't want to increase the scope of my analysis because I have been given a tight budget, let's say, to perform my optimizations here? Then will you remove that instruction if there is a label on that instruction? No, right? So if there is a label on this instruction, unless you have increased the scope of your peephole and figured out that there is no jump over here, you cannot remove it. If you have not done it, you should not remove it. We usually don't do it, we'll just leave it, right? So it's not, again, the idea is not to come with the best possible code, but try out heuristics here and see. And what's the heuristic here? The heuristic is, oh, I'll only look at the same basic block. I'll miss some optimization opportunities, but I'm fine. If I know that I can still optimize code significantly without looking outside the basic block, and if the trade-off is to analyze a much larger piece of code and instead just perform multiple passes of some quick analysis, I'll prefer the latter if I am in a peephole pass. Make sense? Okay. So yeah, one may ask, why would this code come in the first place? Yes. Right. Correct. Right. Yes, because now this is the state of the code, right? So you are answering my question partly. Why would we have such a stupid code to begin with? Oh, the programmer did not write such a stupid code. The code generator, even though simple one-to-one mapping, it will probably not generate this stupid code, but maybe some other pass, as you said, there were other instructions in between these two, and some pass deleted those instructions or moved them somewhere else and so on, which had no dependence on these. So now these instructions have come together. Now if there is no label to the second instruction, or if there is a label and I have figured out that nobody is jumping to that label, I can remove the second instruction. Mitesh, does it answer your question? Yes, again, so you may have to figure out if if there is nothing in between, then you are sure that A will still contain the same value, right? So even if somebody uses A in future, that's not a problem, right? Because it's the same value in A if these two are the instructions next to each other. So a peephole optimizer will, I hope I see you all have seen more powerful optimizations already, as I said, and hence you have to kind of limit yourselves to realize why are we also looking at peephole optimizations if we have performed the previous ones. The idea is, oh, there are many optimizations which have got enabled as a result of other optimizations which can be performed just by looking at a small window now. Okay, that's the idea over here. You would also hear about, as we will discuss later, you would also hear about JIT compilers many times in future. Nowadays, JIT doesn't exist only in the context of Java-like languages. There are JIT modules in LLVM, in many other programming languages, where some part of the code you have postponed its generation to some later point of time, right? So let's take some example. If I am working with C, where I generate code and then run it again any number of times, I am okay in spending a lot of time in generating the code. But if I am generating code in a compiler which has been invoked just during program execution, let us say, then I'm not okay with spending too much time at that point, because somebody is waiting for that code's output, for example, right? So there are compilers where you don't really have the budget to perform complex analysis passes. Okay, so that's one more thing to keep in mind over here. Anyway, so yeah, this kind of a code may not be there in the beginning, but it may come as a result of some other optimization that may have happened. Okay. All right, there are more examples. So you have seen unreachable. Have you seen unreachable code elimination in the previous classes? So if you have, for example, a branch that cannot be reached, if there is a conditional which is guaranteed to be false after performing constant propagation, that branch becomes unreachable. In fact, a lot of people perform unreachable code elimination on big packages. How many of you use JavaScript? Yeah. So when you create bundles, has any of you tried to create bundles? Have you used these bundlers? So when you create a JavaScript application, for example, and let's say you have imported lots of libraries, right? And now when you want to bundle this application into a small package and send it across over internet to somewhere, let's say you don't want code of that part of the code of the libraries that you really don't use in this application, right? So you imported it, you install lots of dependencies, let's say, and then you don't use a major portion of those dependencies. Now if you want to bundle this together and send across, or even the Docker image that you are going to use today, I installed, let's say, Python 3, full Python 3 and along with its libraries, but I am using only some 5 Python calls in let's say the assignments that I give to you, then I don't need to really keep that whole thing in my image, right? So unreachable code elimination is extremely useful when you want to bundle things in a small package and send it across, okay? Particularly when you are using libraries that may have thousands of functions available for users to use and so on, and you are not going to use most of them, right? In some sense, statically, if you can figure out what things you would never use, you can just remove them, right? Yeah. So whether you have linked or not, doesn't matter whether you linked to that code or not, but you know that what code you would never touch, for example, you can remove it, right? So that's standard unreachable code elimination. The same unreachable code elimination has a peephole version as well, just by looking at small windows again, right? So let us say I have code like this. What's unreachable here? Inc R0 is unreachable, right? Again, you may say that there should not be a label to Inc R0 that somebody can jump onto. It should not happen that there is some L3 Inc R0 here and there is a go to L3 somewhere else. If that's not the case, then this Inc R0 is unreachable. So you can just remove this. You can just result into this. You don't need that go to L2 as well. Well, there are two things that happen here. First, let's say this code is unreachable. So you remove this. Now you are left with go to L2 and L2. So maybe there is another peephole optimization pass which finds if you have a go to the next statement, and then I can remove this go to. So that pass, let's say, that's another peephole optimization here, eliminating redundant go tos, let us say, and those two combined leave you to this code. You don't need these two lines over here, let us say. Okay. So this is another peephole optimizations that typical compilers perform. I'll tell you a recent experience we had. We are writing a JavaScript static optimization framework at IIT Bombay right now, and it's a first attempt static optimization of JavaScript. People don't usually optimize JavaScript statically, so we didn't want to perform. We just wanted to first establish a claim that it's a good idea to perform static optimization of JavaScript programs. This is the claim we wanted to make in our first attempt right now, because nobody tries to do so. People use engines like V8 and Firefox SpiderMonkey and all of it to optimize JavaScript code. We didn't want to use that, or rather we wanted to tell you could have done better even without going to those expensive JavaScript runtimes, right? So there we found that we could not perform many in JavaScript in the first attempt. At least we could not perform many IDFAs that were useful. Or rather, even if we performed various iterative data flow analysis, the kinds of which you have seen in the last class, we were not able to use them much. Why do you think, okay, before I move ahead, why do you think in a language like JavaScript, IDFAs may not be as useful in a language like C? Let's first try to understand that. No, so I wrote an analysis pass for it, which means I am writing a compiler, you can say, for it. By default it's interpreted, that's fine, but I am writing a compiler. Why would I not be able to achieve much? Excuse me, yeah. Why would I not be able to achieve much by performing, let's say, constant propagation in JavaScript using the data flow equations that you studied earlier, as much as I would have been able to achieve in, let's say, a language like C or Java or C++? Can you guess? The types aren't there. So that's one thing. If you have A plus B, you don't even know whether it's an integer plus, it's a floating plus, it's a concatenation plus. So are A and B strings? That's one thing. So the amount of optimization you can do in general is much less. Second, there is one more. There are closures in JavaScript which can take away variables along with them somewhere else. So resolving scope of variables is very difficult. Saying that if I have a variable A declared here inside a function in JavaScript like languages is not enough to say that it's a local variable. You can have var declarations, let, cons. There are so many things if you have done JavaScript programming that make it difficult to determine the scope of a variable. Right? Which means if you just implement data flow equations as it is without performing these closure level analysis or var-let based analysis and so on, if you have not done all of it, you won't find that IDFAs are really useful in the JavaScript land. So now what do we do? Unless we, as I said, if it's a first attempt and you want to just show that statically something can be done rather than offloading to, or rather than waiting for heavy engines like V8 to perform optimizations, we still were able to show a significant scope for improvement by performing lots of such peephole optimizations. In fact, my student wanted to create a demo which I could show to you. He had to travel, so he could not, but we were able to achieve speedups of 2x on real world JavaScript programs just by performing peephole optimizations, and maybe one more. I think there is some temporal dead zone analysis that helped us do. So one IDFA and then lot of peephole optimizations, some enabled by that IDFA and some others. And we were able to achieve more than 2x speed up on real world large JavaScript programs. No IDFAs, because IDFAs are difficult to do. Now we plan to implement lots of interesting versions of data flow analysis for JavaScript in the next attempt, having established that it's worth spending that effort because we are able to optimize code statically as well. Okay, does that make sense? I hope I didn't confuse you, but at least there are, what you should know is there are languages for which IDFAs are not straightforward. They don't translate very well from the equations that you learned. You may have to add on more, you may have to think through more, it will take more time. If you just wanted to improve something quickly, peephole optimizations are to your rescue. And there are languages where this will suit more.
Since
You're not doing at variable level, right? Now you're doing at register level, for example, right? So you have lowered your abstraction level significantly. You don't need to worry about, now you are only, you have some more guarantees given by, let's say, the limited window that you have, right? Anyway, so yeah, so we could say here that an unlabeled statement, an unconditional jump can be removed. If it has a label, again you need to find out whether somebody else is jumping to that label and so on. You can also do some flow of control optimizations at the peephole level. Let us say I have code like this, like we saw in the previous slide. Go to L1, go to L2, and then you can just replace it with go to L2, go to L2 at both the places, because the previous guy is also jumping there. And when can you eliminate L1 go to L2 itself? So you generated this code now. Can you eliminate this code? Yes, if nothing is jumping to L1, then you can remove that instruction itself, right? So again, you see that one peephole optimization may immediately lead to another peephole optimization within a small window. Right? If you had this code, for example, let's take a high level look here. You had if A equals B, S1, else S2, and then else S3. If you use the intermediate code generation logic that you might have studied in your courses, you might generate something like this. You would say if A equals B, because at the intermediate level you don't have direct jumps, there is no if semantics directly, you have conditional and unconditional branches enabled by gotos, let's say, then you might generate something like this. If A equals B, then go to L1. At L1 you have this S1 now, after that you want to jump to S3, and similarly here if you don't fall through, if you fall through, instead of jumping here you would execute S2, and again you want to go to L3, right? I think some of you would have written code like this if you have studied Dragon Book, or if you have directly written a 3 address code generator. And now what can you do here? Can you do some optimization here? PO3, can PO3 be done over here? Yeah, the second last, you have a go to L3 and then there is L3 falling through it, right? So you could have just removed it and said, oh, L1 is S1 and directly L3 is S3, right? So again, just an example of why such an optimization may have gotten enabled. There are more. Now let's look at it a bit faster. If you have x plus 0 happening somewhere, y times 1 happening somewhere, does it need to happen? Yeah, assuming 0 is identity for plus, x plus 0 does not need to happen anywhere, y times 1 does not need to happen anywhere. And why would such a code exist now? Let's say you performed some constant propagation, you inlined some function, after that you performed constant propagation, and then such equations or such expressions came into being, right? Once such expressions are there, you can now perform a peephole optimization just by replacing x time or removing the expression x times 0 and replacing it with 0, right? If you have a function call, you usually have a power function, right? Power of x comma y. What if you know that y is 2? So you want to do x square basically. If you want to do x square, why do you need a function call? You can directly replace it with x times x, for example, right? Some things like this. Fixed point multiplication and division can be replaced with left shift and right shift if they are faster, as we saw in the previous example as well, and so on. This one is interesting. This is something many compilers do. If you have a floating point division by a constant, you can replace it with a multiplication by another constant. Can you give an example where this would be useful? Why do you think it would be an optimization? Floating point division and multiplication, which one is cheaper? Yes, you have to look at the circuitry, yes. So if you know from that circuitry that multiplication is much cheaper than division in floating point, then let's say you have a division by 2.0. Can you replace it with? Yes, you can replace it with a right shift, or rather first let's say by multiplication with 0.5 and then a right shift, right? So there are many cases where you can replace division by its reciprocal, multiplication with its reciprocal, if multiplication is faster in my floating points. If, of course, after getting the constant you would again get a floating point number there, and if you know that multiplication is faster than division in my circuitry, I could replace it with that, right? So these are small, very small, simple peephole optimizations. As one of you said just now, they are dependent on what is cheaper and what is more expensive on a given hardware, and based on them a compiler usually just performs these as pattern replacements. Very quick, don't need to spend much time building any special data structure, performing any analysis multiple times in multiple passes. You can just keep on doing such passes optimizations. Strength reduction, well, let's say there is a variable v here which is multiplied with I in every loop iteration, and again assuming that addition is cheaper than multiplication, I could have replaced this piece of code with v equals v plus 4 instead of v equals v times I over here. Make sense? This could be another peephole optimization, though I hope you can see that the size of the peephole has increased over here. Well, and you can use specialized instructions. If you have this, move one to a register and then add it to another register, and if you have an increment instruction available, you can directly say increment that register. Move something to the stack pointer, move stack pointer to a register, so save the stack pointer and jump somewhere else. If that's a function, you can directly replace it with a call instruction if that's faster on your hardware, and so on. Right? So let's just look at a quick example which convinces you that after seeing all the complex optimizations and analysis, there is still a lot that real compilers do at a peephole level. Okay, we'll see a demo now. So what's the ultimate goal of any optimization? As we said, improve a few of the metrics, either let's say space, time, and so on, right? So here we'll see one of them. So let's say, is this visible? Is this visible? Can you read this? So let's say I have a C function here, very simple one, which just takes an integer pointer and then stores the same content in itself, and then returns the content of that pointer. Okay. Let me use GCC hyphen O0. Does anyone know what is O0? What are these O0, O1, O2 in GCC? Optimization level. So is O0 more optimized than O1? No, right? So O1 is typically more optimized than O0, let's say. These are optimization levels. They are just telling the compiler, oh, somebody has implemented these set of optimizations, but if someone wants a very quick, fast code, then don't perform them. Use O0, for example, and so on. And what does minus S do? Any idea? This will generate emit assembly. So if I do like this, I'll just get a binary. But if I do like this, I'll get a file foo.s that you can see, that you can read to see the assembly instructions generated for this. Okay, so if let's say we do like this, and I have a foo.s generated here as promised. So if I say cat foo.s here, you got this code. Okay, so this is ARM assembly here, and I don't want to explain everything to you, but SP is the stack pointer, and you had star a equals star a, where a is taken as a parameter. So on ARMS, in ARMS, the parameter is usually, I believe, parameter list, I believe, starts at x0. The register x0 is reserved for it, and the register w0 is supposed to contain the return value. So if you are returning something from a function, if you put it in the register w0, it will automatically be collected in the caller, in the function that called it. Okay, so this is the convention used in ARM, and here we are doing something many times. I hope you can see the repetition here, but here I have the stack pointer. I am storing the content of the number. So number 8 is added as an offset to the stack pointer. Whatever content is there, I am storing it into x0. This will give me the parameter. Okay. Now that parameter has a star to it. I want to get star of a. So I want to again load that address over here at x8 sp plus 8, and then its contents, these square brackets tell content of that register. That content I am storing into w8. So in w8 I got star a, here I got a, here I got star a, and then since we have star a equal to star a, for the right hand side we did star a once, for the left hand side we again want to do star a, right, to find out where do I want to store the value, and for that we again got sp plus 8 here. That content I have put in w8 again, and then I got it once more to perform the store, and I am storing it because here I want to return it. There was a return star A, so return star A again requires me to compute star A. Star A is obtained by adding 8 in this case to the stack pointer and then getting its contents. So I'm repeating the same code here again and again and again, right? Now if you do O1 here, any questions here? So this is just 3 times star A, hence 3 times you are seeing the same code, and W0 contains the return value by default, this register. Now let's say I do hyphen O1 and visualize the assembly code once more. It's so tiny now. What does it do? Forget about the first part. It's just reading the content of x0 into w0 because it knows x0 is the point, is the parameter, and then it just put it into w0 directly because return star a is what I wanted to do. So why do I need to do star a? Star a, it's redundant, right? So what peephole optimizations might have been performed by GCC at the O1 level to do this? Can you have a look at the code above and below and map it to some of the see, the only complex thing is instead of add mul, you see some more characters, LDR in small letters, not in capital letters. So there is some syntax change here, but that's not really important. What optimizations of the kind we have seen in the previous slides might have been performed here by GCC? Redundant loads and stores have been removed, right? Can all of them have been removed in one shot, or do you see multiple passes might have been performed there? Multiple windows, yes. And is it like in one shot, if I look at 2222 instructions, I would get rid of all of those redundant load stores, or was there something else too? Yeah, sure. Let's say it's 2. There was an addition and all also which is gone there, right? So redundant loads and stores, and then that add instruction is also gone there. Add sp hash 16 is also gone there. So okay, I think I can just tell you right now because we haven't really discussed the structure of a stack frame in detail, but you know that when you execute a function, you create an activation record for it, right? When you call a function, you push an activation record or a stack frame for that function on the runtime stack, right? And then the start of this is the stack pointer. The size of the stack is supposed to be determined from the code. Oh, what would be the size of this stack? How many variables are there? How many parameters? How many return values? Based on them, I decide the size of the stack frame. And then at the end, I need to restore the stack frame back to where it was, right? Since here I was doing several computations, I needed space for those many variables on my stack. And then I am resetting my stack pointer to sp plus 16. Let's say I was growing downwards, and then I have reset it back to 6 plus 16 so that it went back where it was. Here I have not even touched it. So I don't need to reset the stack pointer, it's already what it was. I have not used any space in the stack frame over here. So I don't even need that addition over here, right? So it's not required. So that's some more which is not covered by redundant load store removal over here. But I hope you can see that if all of this code goes away, you're not really adding anything to the stack pointer. Your stack frame is actually empty. You don't really have anything here except the parameter and the return value. There are no local computations here, and as you can just get rid of it and return over here. So this is just a very tiny example, but I wanted to show you that even peephole optimizations are performed by real compilers like this here. There is no scope for any IDFA in this example, but a simple peephole was able to give you what you wanted. So that's why it's at O1. If you are at a higher level, you may actually enable IDFAs that take more compilation time and may actually perform more optimizations across basic blocks, and sometimes higher optimization levels may do optimizations across function calls and so on. Okay, all of you with me? Okay. So now let's move to the other set of slides which really talks about register allocation. If you want a 2-minute water break, very quick 2-minute water break, I am ready to give. I want. No, I have. Yeah, since we took a break, right, people optimizations came in like suddenly. Ideally, we should have covered register allocation fully and then come back here, but that's fine. Okay, has any of your friend gone out? Do you know? Should we wait for 1 minute? We have some background music. Oh, they stopped. Anyway, yeah, I think people are coming in. Shall we continue? I think 2 minutes are over now. Okay. So now let's talk about register allocation here. See, instruction selection we have made it a very simple task right now by saying that we'll just do a one-to-one mapping with some cost metrics associated with it. Instruction scheduling we'll see later on. The third task of, or rather one of the most important tasks of a code generator that we would study now is register allocation, because fine, you can generate instructions because all of them are available. You can afford to generate poorer instructions as well because there are some people optimizations that may be performed later on, but you have only a finite number of registers available, right? So where are these registers usually? In a CPU, in a computer system in general? They are on the processor chip, right? So usually registers and some levels of cache are inside the processor chip and then others are outside, and you know the hierarchy, I hope. So the number of cycles required to access registers is much less than accessing the memory and still less than accessing different levels of cache. Okay, so usually anything that's in the register you can access the fastest. Okay, and there is another trade-off over here, that as you go away, you are not inside the chip, so you can afford to create new circuitry for it. Let us say you can create newer memory or larger memory for different components as you go outside the CPU, right? So as you go away from the CPU, you have more space usually, but it's slower to access, right? Which means, again, what logic tells you here is you want to keep the things that you want to access the most as close as possible, so that your accesses to them are faster. So you want to make sure that variables, if possible, all variables should have been in registers before you want to access them, isn't it? It would be so good if all the variables could be accommodated into registers, but again, because of the size constraints and so on, we don't have too many registers here. So it's an important duty of a compiler's code generation pass to identify a good enough assignment of variables to registers. That's what is meant by register allocation. So yeah, again, RISC kind of computers have many registers. Usually the instructions are smaller, 3 address code, simple addressing modes. And in CISC systems, you may usually have fewer registers, variety of addressing modes, variety of instructions, several kinds of registers, and so on. Okay, like Intel x86. There are stack machines also, like Java Virtual Machine, in which the only register in some sense is the top of the stack. There is no separate set of registers available. So usually you would see whether when you write a compiler, somebody would ask you a question, oh, are you writing it for a stack machine or for a register based architecture? Okay. If you are writing a compiler, let's say you are writing, can you give me an example of a stack machine? Which programming language uses a stack machine by default? Java. Java bytecode is supposed to run on a stack machine. It has push pop like instructions, for example, right? So if you are generating code for a stack machine, you don't have to worry about register allocation. That's one thing I wanted to tell. Okay, But most of the times you want to run code directly on a hardware, and most of the hardware have registers in the CPU, in the processor chip, and hence you want to perform register allocation. Okay. Yes, yes. So the stack, that's a very good question. So when we talk about Java later on and just-in-time compilation later on, we'll see that, oh, Java bytecode is for a stack machine, which is the VM, but the VM is running on the hardware, right? So for VM's code, you will have to do register allocation. We'll see. We'll have a look. Please postpone your question until day after. We'll see why do we have this stack machine in between. What can we enable by having a virtual machine in between? That's what we would see for Java. Okay, so hold on to that question for 48 hours. That's too long, but we would see why do we even not go directly? Why don't we generate direct code for direct hardware code for Java, for example? But fine, it enables many more optimizations. That's a small answer, but we'll see it in detail. Okay, so register allocation involves two things. In different textbooks you might see these words, so just clarifying them here. Allocation means which variables to be put into registers, and assignment means which register to use for a variable. Okay, you might see these terms used interchangeably. I am just calling it register allocation, whatever it means. Okay, but clarifying it here. And finding an optimal assignment of registers to variables is again an NP complete problem, like almost everything in the backend, which means you may have to make conservative estimates. You may not be able to come up with the best solution, but we will try to come up with a good solution, right? And then yeah, there are lots of things. It's not just the case that you have a limited number of registers. Many registers have different conventions. Some, like we saw in the ARM example, the return value has to be placed in W0. Which means you can, well, there is one good thing, anything you put into W0 will automatically be used as the return value of the function, but then you cannot leave something else in W0 at that point of time, because it may get read as return value by mistake. If a function doesn't return some value, unless you make sure that nobody is trying to read the return value, you should clear it, for example, or reset it in some sense. And then there are combination of registers used for double precision arithmetic. If you are working with a machine that has only 32-bit registers, how do you add 64-bit values? You will combine two registers. So there are constraints like, oh, if you want to perform 64-bit addition, you have to put the operands in these registers only, because the hardware restricts, or rather allows these two to be taken together as a single 64-bit value. Okay, so there are some such things. Where should the higher bits be stored, where should the lower bits be stored, and so on. So there are lots of such constraints that we need to keep into mind while performing register allocation. So the interesting thing is, as I said in the beginning of today's lecture, register allocation is performed based on something you are very familiar with. What is liveness analysis? What is its goal? Can somebody say it in one sentence? Yeah, what is meant by live? Whether it is used in future, right? If something is alive in liveness analysis lingo, then it means it may be used in future. See, I am using the word may. I hope you saw why we use the word may over here. Can I say that if a variable is live, it must be used in future? Or rather, okay, yeah, if somebody presses Control C in between, then it will not be used in future. But what if there is a branch afterwards, right? I hope when you wrote these data flow equations, you saw a merge function, and that merge function basically takes care of possibilities that may happen in future. Here it's a backward analysis, which means if I have a conditional, and in that the true branch of that conditional, the variable is used, but in the false branch it's not used, I would still say that the variable is live before this point of time, right? So if I have a conservative estimate of live variables, see, everything statically becomes a conservative estimate, because it may be used, it may not be used in future, but if it may be used in future, that variable is live. Okay, so that's one thing. That's what you learned about liveness analysis. And why is it interesting for register allocation is because if two variables are live at the same time, then they cannot stay in the same register, right? If I have two variables A and B, both are going to be used in future, I decide to put A's value into register R1 and B's value also into the register R1 at the same point of time, I cannot do so unless I have packed both the registers and access half of it and so on. That's fancy stuff. That will come at the end. But let's say each register has one variable. I cannot assign two live variables the same register at a given point of time, right? And that's why liveness analysis is interesting over here. We would say that if two variables are live at the same point of time, then they interfere with each other, okay? And if two variables do not interfere, conversely, then they can use the same register. Yeah. So if two variables are not live at the same point, that means they can be assigned the same register if you want to. So need to determine the durations in which variables are live. Let's see. So if I have this program here, I have 6 statements here, 3 variables A, B, C, and let's say n is some constant. I don't care about n right now here. It's not constant, it's some global variable, let's say. So I care about these small letter variables A, B, and C. And I want to decide how many registers do I need to execute this piece of code, let's say. So can you tell me the live ranges of all the variables in terms of the statements? Can you tell from which statement to which statement is A live, for example? 1 to 3? No? 1 to, no. 1 to 2 and then 4 to 5. How do you tell that? If you were writing liveness analysis as a data flow analysis and you would compute in and out sets, right? Yeah, so I hope you see that we are coming from there directly. How will you say it's not live between S2 and S4? Right, so it won't be there in the inset of this statement, right? So from the in and the out sets, you can determine the ranges in which variables are live. So here you can say A is live from S1, S2, or in the range S1, S2, and then in the range S4, S5. What about B? S2 to S4, after S4 it's not live, and C? S3 to S6, right? So let us say I have drawn I have determined the live ranges of all the variables like this based on in and out sets that you know how to compute from liveness analysis, right? Now let's draw a graph. So in computer science, in compilers at least, most things work on graphs. Most common representation for doing anything is a graph. Can you help me make this, establish this statement? What do you use for lexical analysis, which is a graph? Finite automata. Lexical analysis, AST comes later, right? You work with a finite automaton. Isn't a DFA or an NFA a graph? Yeah, regular expression can be converted to a finite automaton, which is a graph. Syntax analysis, AST, is a tree a graph? Yes. Intermediate code, well, you generated 3-address code, but many compilers also generate some graphical 3-address code. But anyway, once you generated intermediate code, what did you convert it to for performing analysis? Control flow graph. Similarly, when you generate code, one of the popular ways is to use a DAG, a directed acyclic graph, to generate code. We didn't study it yet, but that's a graph. So we will use, for register allocation also, we will use a graph called as an interference graph, right? So we have the live ranges of each variable determined in the previous slide, and whenever somebody uses the word graph, you should first ask the question, what do the nodes represent in that graph and what do the edges represent in that graph? So the nodes of this graph, interference graph, will be temporaries or variables in your program, and if the live ranges of two variables u and v overlap, then you would draw an edge between u and v. So an edge denotes interference, right? An edge denotes interference here, right? So yes, so if there is an edge between two nodes representing variables u and v, they cannot be mapped to the same register, right? That's what we would do over here. So we would perform liveness analysis. First we would generate control flow graph from this program, then we would perform liveness analysis using in and out sets. We would determine live ranges of variables like this, and from this we would draw this interference graph. These are the steps if you have to implement it, right? So now if let's say I draw a graph here, there is an edge between A and C. Why? Their live ranges interfere. A is live from S4 to S5 and C is live from S3 to S6. These are interfering, and hence there is an edge from A to C. Similarly, there is an edge from B to C. there is no edge between A and B because A is live here and here, whereas B is live from here to here. These live ranges do not overlap, and hence there is no edge between A and B. All of you with me? No confusions here. So I have drawn, let's say, this interference graph, and now we would color this graph to perform register allocation. You might have studied in your data structures and algorithms courses graph coloring. What's the graph coloring, standard graph coloring problem that you solve in those courses? Color a graph with fewest number of registers, fewest number of colors, let us say. If a graph is k colorable, what does it mean? You need a minimum of k colors to color all the nodes of that graph, right? Here, what would it mean? Minimum k registers. So if I can color a graph with k registers, I can solve the graph coloring for problem for an interference graph using k registers. It would mean that for the program based on whose live ranges I drew this interference graph, for that program I can work with k registers. K registers are enough. Okay, so let's try to do that. Yeah, so two nodes that interfere with each other must use different colors. If they don't interfere with each other, then they can use the same color if there is no edge between them, right? So if I had this ABC, A and B do not interfere with each other, so they can use the same color here, let's say blue here, and this one is orange, let's say. And what does this mean? You can assign A and B the same register R1, and you can assign C a register R2. What do we mean by that? What would your, so let us say this is the outcome of my register allocation algorithm, that okay, you need two registers. Let's use the pen a bit here. A and B can be given R1 and C can be given R2. This is the outcome of my graph coloring based register allocator. Now what is it useful for? This was my original code, right? Yeah. How do I use that information now? How do I use this information now? What do you mean by register allocation? I want to show it to you here. So if I have A and B mapped to R1 and C mapped to R2, you can directly, let's say, first replace this. A equals 0, R1 equals 0. B equals A plus 1. Just replace B with R1. R1 equals R1 plus 1. Very good. Next, you are seeing, I hope you are getting surprised by this. This is more interesting than what is written there. Then C equals C plus B. What would I write? R2 is equal to R2 plus R1. Of course, that means R2 should have the original value of C. It's coming from somewhere, let's say. And then A equals B times 2. R1 equals R1 times 2. Then n equals a plus 3. Let's say n is some memory. I don't want to assign a register to it. N equals R1 plus 3 and return R2, right? So this is the code after performing register allocation. Well, these R1, R2, R3 are not really variables in my program. They are registers on the machine. So what would you do after this to convert it to machine code? No, then we are going back. We came from variables to registers. This is just a representation, right? Because this is not valid code. R0 variables A, B and C were there in my scope, let's say, as declared variables. R1, R2, R3, or all these are not variables declared in my program. They are at a lower level of abstraction. They are from the hardware. So after this, I could do instruction selection. Instruction selection. And then I could convert something like, oh, if I see this, I would say move R1, 0. If I see R1 equals R1 plus 1, let's say I decide to do inc R1. R2 equals R2 plus 1, add R2, R1. Based on, again, your hardware, left to right or right to left, that you know from your vendor's specification. Then once you see R1 equals R1 times 2, you have a choice. Even with a 1-to-1 mapping, you have a choice whether to multiply by 2 or whether load 2 into a register and then do something, or left shift, for example. So let's say we have shift left available or left shift available. So shift left R1 and then some add, n is something special, and add, no, so you need more here. It can't be a one instruction for this. You have to first add R1 to 3, right? So let's say you have add R1 comma 3, and then you have store n R1, and then let's say return L2 R2, and let's say we also have a special register called as X where you can store the return value. So you can just say move X comma R2, right? So this is after performing register allocation. After mapping variables to registers based on the hardware that you have, you can just generate some instructions. You can select instructions wherein you will bring in all the cost metrics and so on, and then you can perform people optimizations if you want over here. After performing those people optimizations, you can also schedule these instructions on in different times that we are yet to see. But I hope you see where are we right now. Register allocation is typically the first step, okay, which we are studying in detail now. Any questions till now? So in the assignment that I would share with you in the second half hands-on session, the assignment that you have just does this first step. You would see that you have an input C-like program. It converts that, it performs register allocation based on graph coloring, which is based on liveness analysis, precisely what you know already. And it would do this, replace the input program with something like this, where it will replace variables with registers. This is what you would get as the output of the code that we'll share with you and you will play with. Give it different kinds of programs, draw different kinds of interference graphs. It will also show you the interference graph, match it with your understanding, make sure you understand everything concretely. But this is that part, okay? I hope that's clear now. Now there is one interesting thing. What's our target here? When we perform register allocation, and let's say my machine has k registers, there are two things which we will look into now. One is how efficient is to find a register allocation that only uses k registers. Is it even, and then second is it even possible to have only k registers? What if my program requires more than k registers? Okay. Now, so graph coloring is an NP complete problem again. So if you use graph coloring based register allocation, there is no guarantee that if you have k registers, every program can be register allocated using k registers. There is no such guarantee. You can't come up with such an algorithm that does that. And can we efficiently find the optimal coloring of the graph that is using the least number of colors? But we probably don't need the perfect coloring is something you should consider here. If my hardware has 7 registers available without constraint, and if my program ends up using 3 versus 5, does it matter? Probably not, right? If I am using 3 registers versus 5 registers and both are less than 7, I probably don't care. Okay. That's one thing to keep in mind. You may not always want to find the best possible solution, the least number of colors to color a graph. That's not really required many times here. Similarly, you would, since there is no best solution or there is no guarantee, you may have to come up with some approximation with heuristics here, right? So the next question is what to do when there aren't enough colors. So let's say I had a program, I had only 1 register available for this piece of code. What do I do? Here I was able to color this graph using 2 colors R1 and 2 registers R1 and R2 or 2 colors blue and orange. What if 1 register was already occupied for some other live variable which I can't remove? Push it to memory. Do you see that? If I have 2 contenders for a register, the only thing I can do is to keep one of them in the memory and load it directly from memory. What does it mean? Its access will be slower since it's in the memory, not in a register. I can't keep it in the register. Its access will be slower, but it would have been good if I am using 2 variables, 2 are at this, okay, so one of them will have to go to the memory. Which one? If I have 2 variables and I have space for 1 in a register, which one to keep in a register? One which has least, you might want to say one which is used the highest number of times you may want to keep in a register, for example, right? So such a metric you would have to come up with when you have to decide which variables to keep in the register, and the other one has to be sent to the memory. As you said, that process is called spilling. Okay. Spilling is a compiler's term here, and we say moving this variable to a memory is same as spilling that variable. Okay. We spill it to the memory. Note that if you spill it to the memory, you have to remember where you have spilled it, because if you spill it somewhere, next time you see the variable being used. Here we said that okay, once we decided that A should be in R1, wherever we had A in the code, we just replaced it with R1 blindly. But what if I had decided to spill A to memory? I will have to remember the address, the location where I have spilled A, so that whenever I see a use of A, I will load that. When I select my instructions, I will add a memory access instruction there to access the variable from that memory location. Make sense? So instruction selection has to go hand in hand with the output of register allocation, because if something is not in a register, you have to select memory access instructions to access that instruction. All of you with me? Okay, so we need to add instructions to spill it, to store it into the memory and retrieve it from that memory location whenever we see that variable in the program later on. Make sense? You people look confused, you too. Oh, okay. So there are ways to color graphs here that we would use first of all. I hope you have seen all the challenges that we have to address on the way, but now let's try to color the graph. So we still want to color it with few colors, so that so one may ask, then why, if we cannot come up with the least number of colors, it's all NP complete, and it's okay to not use all the registers on the machine and so on, why would we still want to color with as few colors as possible? It's because, oh, maybe I am performing register allocation over a small piece of code without looking at the remaining code, and if I very freely use registers and all those variables are live, let's say I perform register allocation over the next window, I may not have enough registers, I may have to spill more. So it's still a good idea to target the usage of registers as optimally as possible. Okay, so that's one thing to keep in mind. With that, let's try to color a graph. So what a typical graph coloring approach does is, you have the interference graph, remove a node and all its edges from that graph, if such that the degree, okay, for all variable nodes whose degree is greater than the number of registers that you have, you, let's say, remove all those nodes from the graph. Why do you think that would be useful? Because if a node has a degree higher than the number of registers I have available, what does it mean? It interferes with so many variables. That means all of these, me and my neighbors, all of them cannot be assigned registers together. I interfere with all of them, and the number of people I interfere with is more than the number of registers, which means I am a troublemaker for a register allocator, right? So this algorithm says, first remove all the troublemakers. Okay. All nodes that have a degree greater than or equal to k, just remove them. Simplify the graph so that troublemakers are gone. Let me handle the ones that I can handle easily, whose degree is less than k, for example. Okay. So after this step, G is either empty, either all are gone, or I have all the nodes whose degree is, sorry, let me, ulta. When you have a troublemaker, you want to handle them first. Okay, think of it as a greedy algorithm, right? So if I know that a node's degree is less than k, I should remove it first. Okay, I'll worry about it later, because anyway it does not interfere with k registers. So let me handle the ones that are troublemakers first, whose degree is greater than equal to k. So now at this point I have only all those nodes whose degree is greater than or equal to k, and now take a node m and all its edges out of G and mark it for spilling, which means these are ones I cannot allocate registers on. I'll handle only the other ones for register allocation. Yeah, that's how I wanted to say it. So just keep repeating this step until you have until you have removed all of them, and then allocate registers to those for which you have a guarantee that you would be able to allocate registers, because they had a degree less than k, right? So now let's try to use, this was one of the oldest graph coloring algorithms proposed in the initial compilers of Pascal and Ada and old programming languages. So now let's try to see how does it work. Is this graph too colorable with our algorithm? So what does our algorithm do here? It removes all the nodes and edges with degree, yeah, more than or less than, that's what I get confused about. Remove a node such that the degree is less than k. So first get rid of those which you think you can handle later easily. Okay. So let's pick something. Our k is 2. We have a duster. Oh, it's there. Not topological in some sense. Topological means you are always starting from the root, right? We are not, the root need not have less than degree k here. It's not topological. So let's see, we'll just work out one example. Let's say I have A, B, C, D, E, and now my algorithm says, oh, remove the one that you are sure about. So which of these has degree less than equal to less than 2, less than 2? C, E, D. So let me choose any of them and remove it. Let's say D, and I note down D here. Because I know that D I will be able to allocate registers, it does not interfere with K or more neighbors. Then I have E here, so let me list down E. Then I have C and B, well both have become, so I can just say C, and then let's say B and A. So my graph became empty, right? My graph became empty here, and then our step was, oh, then try to allocate registers to one of them in order. So now let me try to allocate registers. I have, let's say, registers R1 and R2. Let me take one from here. Some people push it on a stack, so they'll take it from in the reverse order. So let us do in this order. Let's say A is assigned register R1, right? And can B be assigned R1 now? No. So let's put it into R2. C similarly cannot be assigned R1, so let's put it into R2. Since this is in R2, D can be assigned R1, and since this is in R2, this can also be assigned R1. So is this graph too colorable as per the algorithm that we used just now? Yes. So that means two registers can be used to perform register allocation for a program that led to this interference graph. Not really. So I don't know why are you calling it topological. This is not a directed graph. There is no designated route here, if you think about it. Makes sense? A is not the root. There is no root in here, right? So it could be any random variable, right? I could have drawn it in a bit such that B looks like the root. So it's an undirected graph. Don't worry about topology here. What about this one? Is this graph too colorable? Can you work out now with this algorithm? Don't work out based on intuition. First, just based on this algorithm. Based on intuition, I'll ask you a more interesting question. That's why. So based on our algorithm, which node will you remove from this? Which node has degree less than 2? D. So D is pushed onto the stack, let us say. And then can you remove any of them? No, which means you would mark all of them for spilling. That's what our algorithm said here, right? If G is not empty, then take a node M and all its edges out of G and mark one of them for spilling. That's why it's not so poor, but it says take one of them and mark it for spilling. So we have, once you remove D here, we have A, B, C, E left. It says take one of them and mark it for spilling. Which one? Let's choose one. B. So let's take B and mark it for spilling. Now we have a repeat until loop outside, right? So now we can try to again remove on the stack. We have one node, so you can assign a register to D which was on the stack, but then before that we have a repeat until loop, which means you can go back and try to remove non-trouble making nodes from there, right? So now just imagine here you have D and B gone. Is there any node left with less than 2 degree? A, C, E are left. So which of them? Yeah, so A and E can be pushed onto the stack, and then C also can be pushed onto the stack because it has less than degree 2. But how many nodes did you mark for spilling here? 1. Which one? B, let's say, any of them based on how we choose randomly, let's say B, and the graph is not two colorable thens. Whenever you load B here, you would end up referring to it from the memory, right? But is this graph really two colorable? Now forget about the algorithm. Can you color this graph with two non-conflicting colors? Can you say how? Let's say D gets R1, B gets R2 because it cannot get R1. Since B got R2, A and E can get R1 and C can get R2 because it doesn't interfere with B. So this graph is indeed two colorable. So this algorithm was a way of performing register allocation, but for this graph it's not giving you the optimal coloring. That graph will say that algorithm will say, oh, you need minimum 3 colors to color this graph, but we see that here that 2 are enough, right? So looks like such a pattern was observed by people many times, and then most compilers that use graph coloring use somebody called Kempe, who existed before compilers existed or programming existed. He in 1879 had come up with a tweak in the original algorithm to reduce spilling, and that tweak was adopted by a person named Kaitin in 1981. So before 1981, people would mark, compilers would mark one node for spilling over here. Then somebody realized, oh, I can just change my algorithm to use Kempe's heuristic and I can avoid that. So what did they do? Can you see what change happened here? This is Chaitin's graph coloring algorithm with Kempe's heuristic. And can you figure out what's the intuition here? So red parts are new here. Instead of taking a node here and marking it's for spill, we are saying push it onto the stack. Stack has those nodes that we were trying to allocate registers for, right? Here I am saying that even if it's a troublemaker, first of course take care of our non-troublemakers, but even if it's a troublemaker, push it onto the stack. That's it. And then perform register allocation directly from the stack instead of marking them for spilling early on. What's the intuition? It's a very small change, and we will see that it allows us to color the previous graph. But what's the intuition behind this? Can you think? We were marking a node for a spill too early in the previous version. We were being too conservative. As soon as something has degree greater than equal to k, we took one node and marked it for spilling. But it's possible that it doesn't. This node may interfere with k neighbors or more than k neighbors, but the other nodes may interfere with fewer people, and hence you may be able to color the graph with fewer colors still if you gave a second chance to it in some sense, right? So that's what came from Kempe's heuristic. So now can we two color this graph based on our new algorithm? You push D onto the stack. Then from the remaining ones also you push one of them onto the stack. Push on stack instead of eagerly marking for spill, and that's when you can keep on pushing all of them for stack, take them out one by one, and you would be able to allocate them registers, two registers R1 and R2. What about this one? So no need to spill. If you used that algorithm, you would not have to select memory store and load instructions for your program. That's the idea here. What about this graph, the second one? Is it too colorable? Even with our improved algorithm? No, right? So here you will have to mark, since B and C also interfere with each other, even after you remove one of them, you would still have a degree with a node. Even if you remove B, you still will have interference between C and B later on, so you won't be able to assign them the same registers, which means these three definitely require different registers, right? So you would end up using, you would either end up using 3 registers if they are available, or if the hardware says no, I have only 2 at this point of time, then you would have to spill one of the variables. Again, which one to spill? Many compilers will just choose any one, But if you want to improve that heuristic, how can you improve? You can try to figure out which of them is used more frequently in future. Maybe if one of them is used inside a loop, then with a high chance that one will be used more than the other one. So maybe spill the other one, not this one, because then you will have more memory accesses, for example. Okay. So there is one more final thing in graph coloring based register allocator, which is called coalescing. So see, we are talking about what many real compilers do. There are two kinds of register allocation algorithms. One is graph coloring and another is linear scan that we will study in the second half. But if I say that a given compiler uses graph coloring based register allocation, I have only told half of the story. There is also a small optimization called as coalescing used by most compilers that do graph coloring. Okay. So coalescing says if there is a copy statement x equal to y and x and y do not interfere, their live ranges do not interfere, then we can use the same register for both x and y, isn't it? Why do we need this copy instruction? If they don't interfere, I can just use a single register and remove this copy instruction, isn't it? So that's an optimization. How is it accomplished is you merge the graph nodes for x and y into one node. Right? And of course, later on while selecting instructions, since you have assigned them the same register, what kind of instruction will you get? See, I had a equals b, and let's say I decided to allocate r1 to a as well as to b. Now when I do instruction selection, what instruction would I generate? R1 equal, well, okay, before that, after register allocation, this is this. And then if I do instruction selection, what would I generate? Move r1 comma r1. This can be deleted very easily by a peephole optimizer. Gone. So finally this will get deleted, and I would now, while performing register allocation, let us try to coalesce the nodes of A and B into the same node. What do we mean by coalescing? Merge them. If you merge two nodes in a graph, what happens to their neighbors? So A's neighbors and B's neighbors both should be there in this node, right? So it's good. Coalescing in an interference graph is good because it reduces the number of registers and we can remove such move instructions. So we can get rid of, if we gave them two different registers, then I will have an instruction move r1 comma r2, let us say, which I cannot remove trivially. But if it is move r1 comma r1, it's a waste instruction I can remove. So coalescing helped me over here in terms of reducing the number of registers and removing move instructions. Can you say why it could be bad? Yeah, no, whose live range? No. Okay, yeah, and how? Right, so if A and B had different neighbors, once you merge A and B together, you may have gotten more neighbors. If you got more neighbors, that means you might be interfering with more number of nodes, which means later on register allocation may get problematic. Right? So there are many such decisions you have to make. In the compiler's world, you would see many times you propose something and then you realize, oh, it's good in these scenarios, but it's actually bad in those scenarios. Now how do I handle this while adding something new in my compiler? So I came up with coalescing. It allows me to reduce number of registers immediately and remove a move instruction. But if the degree increases, then it actually would have it could lead to less more register pressure because of the combined node having more neighbors, right? How may you want to improve the situation then? If you want to use coalescing, under what circumstances can you put constraints? Like anything in compilers, would you like to add some constraints and say, I will coalesce two nodes at a copy instruction x equals y only if dash. Good, very good. So Jayashree says if the number of combined neighbors is still less than the number of registers available, then no problem. I am not adding a troublemaker over there. Anything. So this is one good heuristic. Any other heuristic? See, these are not empirical heuristics. I want to make it clear. We are not running something and saying, oh, it ran better, hence this is the best machine learning algorithm, so get me a paper. No, it's not like that. It's based on intuitions. right? So this is a very good intuition that, oh, combined degree should be less than k. Any other intuition?
Combine and see if before combining and after
Mm-hmm.
less. So if it's more after combining, then
Mm-hmm.
it's worse.
Yes, yeah, but just more is not probably bad, no? Maybe it's bad, as she said, only after, yeah, you cross k. Anything else that you could have checked? We are just talking about heuristics. There can be different heuristics. Think. So same thing people do, So somebody proposed coalescing in, let's say, one of the register allocators as an optimization. Then people came up with and said, oh, there are places where it makes things worse. So let me add heuristics so that I do it only when it's hopefully good, right? So yeah, so there are two options that people have proposed in the past. First, coalesce them only if combined they have less than k degree. Okay, that's one of them. And similarly, people have said, oh, if all of the nodes already interfere with all the nodes that the other guy interferes with, if the interference is a superset, maybe the degree is greater than equal to k, but I am not introducing new interferences. So the degree is greater than equal to k because it was already greater than. So whatever is the degree, I am not adding new interfering neighbors. So in that case also I may be okay with uh, coalescing them together, right? So these are two heuristics, if we may use that word, proposed by people, and most compilers that perform register allocation, if they use coalescing, they'll use one of these heuristics and try to decide which one is better. Okay, so let's stop here by saying that register allocation is quite expensive. See, coloring a graph is, even though this was a 4-node graph, coloring a graph is not easy. Coloring a graph, can you compute its complexity? I can't, you compute. So it's an expensive step. Okay, so it basically takes time quadratic in the number of live ranges if you compute it. So because at any point, see, I'll give you an intuition if you want to compute it at home. So at any point of time, in order to allocate registers, you are depending on how many live ranges do you interfere with, right? So take the cue from there and you would come up with something that says it takes time quadratic in the number of live ranges in the program, in the worst case, right? So there are compilers that cannot afford spending so much of time in performing register allocation, and hence many compilers use linear scan register allocation, which would just take a linear pass over the program, okay, instead of taking time quadratic in terms of this. This was proposed by Massimiliano Poletto and Vivek Sarkar in 1999. So I hope you are seeing the natural progression. First, just plain graph coloring, let's say. Then in 1989, somebody told I can use Kempe's heuristic to do better. Then somebody would have said I can coalesce. Then somebody said, oh, I should not coalesce under these circumstances. And then someone said, okay, all of this is fine, but it's still expensive. Can I perform register allocation much faster, which is nearly as good as graph coloring in many scenarios, but bad by this much in some other scenario, and so on. So, right. So, if we get time in the evening, I would like to teach you linear scan register allocation again. It would take 15 minutes and so, but we'll do it after the hands-on. In the hands-on, first we'll study graph coloring based register allocation, we'll practice it, and many compilers choose to drop that and instead use this linear scan register allocation. So, we'll see it quickly as well. Yes, Jayashree. Good question. They don't construct a tree, but once you say so, I think so. So there is a subtle difference in graph coloring. You would have seen that we were maintaining live ranges. Something is live from here to here, and then something may be live like the variable a, right? Whereas we would see in linear scan that we will just consider the first and the last point. So each variable will have only one range. So the number of ranges would be proportional to the number of variables instead of the number of program statements combinations. Not really, not exactly. It's as you would see, the improvement here comes from the fact that the number of live ranges we consider has been reduced. Right? It becomes linear in terms of variables. But fine, maybe somebody can come up with a version of graph coloring that you said. or maybe somebody would have come up with, I don't know, but that's possible. Any other questions? Okay, so let's end here and we will pick up exactly at this point once we come back after the lunch break. We will start working with the assignment and we'll try to understand control flow graphs, live ranges, graph coloring, register allocation, all of this using that hands-on. Okay, see you. Then we'll finally end by looking at linear scan register allocation. You may want to just quickly search at some point and find out. Just open your phone and find out sometime which languages compilers use graph coloring and which ones use